Interesting semester. Trying to figure out who you're talking about. I had several interesting characters. That was a wild class too.
Stephen and Greg and MJ say hi.
Oh yeah, tell them hello. Are they transferred out already?
Yeah, they're at YouTube. So.
Okay. Yeah, tell them hello. All right, let's get down to business. So last class I postponed or delayed one class, the mini exam. So instead of being due Wednesday, it's now due a week from today. And then on Wednesday, I'll probably hand you the next one, all right? This Wednesday, I'll hand you the next one. So we're going to jump right into 10.5 in terms of our calendar. Let's see here. I think we are still a little bit behind. Yeah. So today, 22 years. It's been 22 years since 9/11. Wow. So we were supposed to start lines and planes last time. We're going to start it today. So we'll be a little bit behind still.
I was curious how many people you were alive when it happened.
Yeah, I don't know. Some weren't for sure. All right, so we're going to talk about equations of lines and planes. These concepts are going to be with us through the rest of the semester. I've told you this already. Chapter 10 is about laying the framework in three-dimensional space so that we can do the calculus in three-dimensional space. So we need to understand, specifically for this section, how we will deal with lines and planes in three space. So right now, coming into this, we know that to define a line, what do you need? 2 points. So on a flat sheet of paper or in three-dimensional space, if somebody gives you 2 points, you have a unique line, right? As long as those 2 points are distinct, right? So to define a line, all you need are 2 points, yeah? Okay. Is there anything else other than 2 points that you could have to define a line? 2 points will work, but is there something else? How about 1 point? 1 point isn't enough, right? But how about 1 point in one other thing? That would be a second point.
X equals 1, that's a line, right?
So if I give you 2 points, right, there's only one line that goes through those. If I give you 1 point, I would have to also give you the slope of the line. The slope of the line, right? If I gave you that and I gave you the slope, then you could always find another point, right? Couldn't you? Like if I said, hey, go there, and then the slope is 3. You go up 1, 2, 3 over 1, and then you could draw a line, right? So back in college algebra, we learned that if somebody gives you a point and a slope, we have a point-slope formula of a line. If somebody gave you 2 points, you could find the slope, and then you could use the point-slope formula. So that's what we used in college algebra. We're going to completely redo that idea, but we're going to do it using vectors, all right? So here's the development of this, all right? So preliminary concept, this is just to make sure we all understand something geometrically here. If you're given 2 vectors, r sub 0, or I'll say r naught here, r naught and r1. So we're given 2 vectors. If we compute r1 take away r naught, the resultant vector is equivalent to the vector from the tip of r naught to the tip of r1. Okay, what? How am I talking about? So if I have a vector, let's say that that's r1, and then I have another vector over here, that's r naught, right? If I want to find r1 take away r naught, then what I'm going to do is look at it this way. R1 adding the negative or the opposite of R naught. That's the same thing, right? So how do we add vectors? Parallelogram law, right? Parallelogram. So I'm going to come over here. I'm going to take negative R naught. That's negative R naught, right? Because I need that over here. Negative R naught is R naught but pointed in the opposite direction, yes? And now what I'm going to do is vector addition. I need to attach attach the tail of the red one to the tip of that one, or the other way around. Doesn't matter which way I do it. So imagine taking this, moving it, I'll move it like that and put it right here. That's R naught negative, right? And the resultant vector is the vector that goes from here to here. Okay. That's R1 minus R naught. Okay? That's geometrically what we have. And what I'm asking you to see is that this resultant vector is equivalent to the vector from the tip of R naught to the tip of R1. So let me try and make that clear. Let me draw R1 again. Here's R1. Okay? And now what I'm going to do is I'm going to take R naught, which is this vector, and I'm going to attach it right here. I should put this on top. There's R1. I'm going to take R naught and put it right there. Do you all agree that's kind of like R naught right there? Tail to tail? Do you all see that this green vector is equivalent to the vector that attaches from the tip of R naught to the tip of R1? My drawing's not that great, but that vector is the same as that one. So give me a vector, R1. Give me another vector, R naught. Subtract. And what you wind up getting is a vector that goes from the tip of R naught to the tip of R1. That's the takeaway. We need that for what I'm about to do. Yes? Okay. Here we go. Tip of R naught to the tip of R1. All right, so now we want to talk about a line. So we know that we're going to start in two-dimensional space, but this extends to three-dimensional space. So this is a line, right? We have a line. All the points that live on this straight line. And what we're going to do is we're going to realize that for every point on that line, there is a vector that goes from the origin to that point. For every point on that line, right? So every point on that line has a vector that corresponds to it, yes? And because of that, we could, instead of defining this line using our good old-fashioned like y equals mx plus b, we could define the line to be just the collection of all the vectors that point to all the points. So some way of somehow defining all these vectors. Make sense? So how do we do it, right? How do we do that? Well, we have to start with something, right? So this is me just saying the vector equation of a line, okay, is an equation which generates all the vectors that go from the origin to every point on the line. So there's an infinite number of vectors there, right? The vector equation of the line is the equation that generates those vectors. So let's focus on just one, just a line, and let's just see if we can't generate one vector. So do you all agree if somebody were to give me a point, okay? So hold on, let me scroll this up a little bit. Okay, if somebody gave us a point on this line, that right there, that point, let's say they gave us that point on the line, x naught, y naught, right? Is it obvious to you that the vector x naught, y naught is the vector that goes from here to here? That could be my first vector. I'll call it R0, right? So that's one vector. I need infinitely many more. All right, so, but somebody giving me 1 point is not enough to define a line, right? They have to give me at least 2 points, right? So now I need that second point. Someone gives me a second point. Okay, now I've got 2 points. I've got R naught, I've got x naught, y naught, a second point, x1, y1. And I can create a vector that goes from here to there, right? And I'll call that R1. So I've been given 2 points, and I've created 2 vectors from those points. And now the cool part. I'm going to calculate R1 minus R naught. And what does R1 minus R naught give me? This gives me another vector that connects from where to where? From the tip of R naught to the tip of R1. So it would go from here to here, wouldn't it? Now, I show that in more steps. So So what I do here is, here's R0, here's R1, and then I create a vector that is the subtraction of those two, and we're going to call that vector V. I put it down here at the origin right now, okay? But that vector can be moved around. I'm going to slide it up, and it's going to go from the tip to tip, right? So there's my V. Yes? All right. So once I've got V, what I can do now is I can get to any point on this line by taking some sort of combination of R0 with V, right? R0 plus V should take me to some place on that line. And so if I take R0 and I add V, I'll be right here at R1. If I do R0 plus twice the length of V, I'll be here, right? Which is another point on that line. But it'll be the vector that goes from here to here. And I can do that for any scalar multiple. I can do R0 and take negative V, and it'll put me back here. Or all different scalar multiples of V added to the R0, and I should be able to generate vectors all along that line. So that gives us a generic formula, which is right there. This is the actual equation of a line, the vector equation of a line in either 2 or 3 dimensional space. So we write R of t, like functional notation, like instead of f of x, we write R of t, and then equals R0. So what's R0? It's like an initial vector. So somebody gives me a point, right? And this vector will come from that point. This is going to be the vector x0, y0 in 2-dimensional space. It'll be x0, y0 in 3-dimensional space. It'll be x0, y0, z0, right? And then t is the scalar multiple that stretches out that vector in both directions. This t is going to be any real number. And then what's v? V is the important one. It's R1 minus R0. So it's what we call the direction vector of the line. So it's almost this equation from college algebra, right? The slope is kind of like the V is. It's like the direction of the line. The x is like the thing that varies. That's the t. And then b is like, this is the y-intercept in 2-dimensional space. Here, this is just some point on the line. So R0 plus TV. T is a scalar multiple. V is called the direction vector of the line. Okay, let's see if we can actually do an example. I'll get back to that in a second, or I'll do this. Let me get some blank in here. All right, I'm going to give you 2 points in 3-dimensional space, and we're going to come up with the vector equation of the line through those 2 points. All right, so find the vector equation of the line through let's go with 4, -1, 2, and -3, 5, 6. What have I given you? 2 points, right? 2 points. And from that, you are supposed to come up with the vector equation of the line. That's the vector equation that will draw all the vectors that generate all the points on that line. So what are we going to use? We're going to use the generic formula, R of t equals R0 plus t times v. Right, that's our generic formula. So we need to just figure out what's R0, right, and what's v. As soon as we have that, we're done. So let's start with R0. What is R0? Where did R0 come from? You remember? It's a vector from the origin to the point. We have 2 of them. Which one? Either one. Your choice. Okay, does not matter which one you choose. So I'm going to choose to label this one x naught, y naught, z naught. That's my choice. And then this one, x1, y1, z1. Okay, that's just my freedom of choice there, right? Okay, so with that, I'm going to define, I'm going to let r naught be equal to that vector that goes from the origin to that point that I've chosen as kind of like my starting point on the line. So what we've done is we've created, I want to be able to show this to you geometrically. Or we have this line sitting in space, right? 2 points that go through this line. What I've done is I've created the vector that goes from the origin to one of those points. Now what I need is a direction vector, a vector that basically is running parallel to this line. And then any combination I put together of those two vectors will be on that line. So we need the v now. So the v is the vector that is going to go from here to here. All right? And we learned how to do that last class, right? Or 2 classes ago, right? The vector from here to here you get by doing this minus that, this minus that, this minus that. So what would that direction vector be for us? -7, 6, right? Because we're doing 5, take away -1, and then last one would be 4. That is our direction vector. And once we have that, we got the equation. So r of t coming here. R of t equals r naught, which is the vector 4, -1, 2, plus t times the direction vector, -7, 6, 4. And you can check for yourself right now that this will give you both of these points. Start by letting t be 0. If t is 0, you get that, right? Which is the first point. And if t is 1, what happens if I let t be 1? You would get, you add these two vectors together, right? So 4 plus -7 would give you -3, and then -5 plus 6 would give you 5, and then 2 plus 4 would give you 6. See? But that's if I let t be 0 and t be 1, I get these 2 points. But if I let t be 2, or let t be -10, or let t be 2.652, or any scalar multiple, it's going to give me all the points on the line, right? Gives me everything. Now, we don't normally write it that way. What we do is we actually put these together. So what I'm going to do here, first I'm going to scale by t on this second vector, which we already talked about scalar multiplication. You just basically multiply through. So it becomes -7t, 6t, 4t, right? And then how do we add two vectors together algebraically? One component at a time. You add the components, right? So you're going to have the first component, the x component will be 4 what? -7t. -1 plus 6t, 2 plus 4t. There we go. That's just me putting it all together. You should be comfortable with both of these versions, right? Yes?
What do you prefer when we write it out?
I don't have a preference. What you should be able to tell, though, is if somebody were to give you this, right? Like, let's say someone gave you this vector equation of a line. You should be able to look at this and tell me the direction vector. The direction vector is just the coefficients of the variable t, right? It's just -7, 6, 4. That's the direction vector of this line. Or if someone said, hey, give me a point on this line, you would just be able to look at that and be like, okay, how about 4, -1, 2? Right? By just saying, oh, if t was 0, right? All right, good? All right. So the next note here, what's going on? When you find the equation of a line, right? When you find the equation of a line, the vector equation, sorry. When you find the vector equation of a line like we've done right here, This really represents the x, right? This is the y, and this is the z, right? So I could actually write down x is equal to 4 minus 7t. I could write down y is equal to negative 1 plus 6t. And I could write down that z is equal to 2 plus 4t, right? These three equations are known as the parametric equations of the line. In other words, if somebody gives you this right here, if somebody gives you this, this is called the vector equation of the line. This, if someone gives you that, that is called the parametric equation of the line. There's two different forms of the same line. And then there's a third version, all right? There's a third version, which are called the symmetric equations. And the way we get the symmetric equations is what we do is we take, let's take this, the parametric. Let me erase this. I don't want to erase everything, but erase that. So imagine if I asked you to take that right there and solve the first equation for t. Take that equation, solve it for t. So we would, subtract 4 on both sides, and then divide both sides by negative 7. That's what t would be, right? Now, I mean, we could simplify that some other way, but I mean, that's right. And then I could do that for the second equation as well, right? So for the second equation, I would have y, I'm going to show the work here, or skip ahead. I'm going to add 1 to both sides, right? And then what would I do? Divide by 6. So I get t as that. That's from this one, right? So solve that for t, solve for t, and then I could solve this one for t, right? That would be z, take away 2, divide by 4 is t. You understand what I'm doing there? Just taking each of those equations, solving for t? So if t equals this, and t equals that, and t equals that, then aren't all three of these equal to one another? So if I write them down equal to one another, we create what's called the symmetric equations. So I write down x minus 4 over negative 7 must equal y plus 1 over 6, but that must equal this last one, z minus 2 over 4. These are known as the symmetric equations. Or symmetric equations. So, yes?
You said that one on the bottom right, that's the vector equation?
This is the vector equation of the line. Yep, this is the vector equation of the line. The vector equation of the line, the parametric equations of the line, and then the symmetric equation. And you're free to use whichever one you want. This is the one we're going to use mostly in here, but you just need to know that these exist. And they all have pros and cons. Like one of the nice things about a symmetric equation is that the denominators here, the negative 7, 6, 4, that's the direction vector. And then if you look at these up here and just take the opposites, like positive 4, negative 1, positive 2, that's a point on the line. But you could have gotten that from here as well, you know, so they all have different uses and advantages. You just need to know that there are 3 different forms of a line now for us. And this is the new one. This is the one that's brand new to us, probably. Okay. So now, what if I change the problem a little bit? And I want to come up with the vector equation, right, for a line, but I don't want the whole line. I just want a line segment instead. Like from one point to another point, I just want to be able to draw those vectors that correspond to the points there. Now, back in college algebra, that's easy to do because If you want to draw a line segment in college algebra that only goes from here to here, then all you have to do is make a restriction on your x, right? And then that would give you your segment. But it's a little harder when the line's in three-dimensional space, right? So the way we do it is as follows. And there are different ways of doing it. I do not follow the book's way. I do it the way that makes sense to me, all right? So let's say, the notes here, I'll show you the note in a minute, but I'm just going to show you with an example. So let's find the vector equation of line from, okay, what were the 2 points I just gave you a second ago?
4, -1, 2.
4, -1, 2.
-3, 5, 6.
-3, 5, 6? Okay. So see the difference between this problem and the one before? Find the vector equation of the line from that point to that point. I should say vector equation of the line segment. Let's put segment here. As opposed to the line that goes through those 2 points. I just want the line that connects the two together. So I don't want you to draw me everything, just draw those. Well, there's great news. You don't have to do anything different except for the very end of the problem. So you do exactly what we just did. What was our vector equation? We came up with R of t was 4 minus 7t negative 6t plus 4t, yeah. Right? That was it? That was a vector equation? But see, in the previous answer, I didn't put any restrictions on t, did I, right? So it was assumed that t could just vary and be any scalar multiple, like any number. Here I'm going to put a restriction on t. And the restriction I'm going to put is that I'm going to let t always be between 0 and 1. Because if t is 0, remember that gave us the first point? And if t was 1, it gave us the second point. And so any number in between is just going to be the points in between those two. So there's a very simple adjustment to what we've already done. Questions there? So just simple domain restriction, and we've got it. All right. So we've done one of those, like, okay. Do y'all want me to work through one of these? Oh, you know what? Let's do this. Let's continue with this problem that we have, okay? Not the one up on the board. Let's just stick with this one. But I want to answer this question. For this problem, for the previous problem, let me write it down here. My question here is, so this is a different problem. I'm going to erase this. Where does R of t equals 4 minus 7t negative 1 plus 6t 2 plus 4t intersect the YZ plane? So let's just back up, okay? So we get to make sure we all are on the same page. Remember, I gave you 2 points, right? And we found the vector equation of the line through those 2 points. So now we can draw all the points on this line. And now what I'm asking is for that line, right? Not the line segment, the entire line. I want to know where, exactly where does this line hit the YZ plane? Where's the YZ plane? Let me see. Red, green, blue, x-axis, y-axis, z-axis. So YZ plane, that's this plane right here, right? I want to know where does this line punch through this wall? Exactly the x, y, and z coordinate of that point.
4 minus 7t equals 0.
So what are you doing? Instead of an answer, what do you need to do? Explain to me.
4 minus 7t is 0, because that's where your YZ plane is, it's where x is 0.
So where this line hits the YZ plane, your x coordinate has to be 0, right? Your x has to be 0. So what we're going to do is we're going to take this, which is our x, right? So to intersect the YZ plane, that implies that your x must be 0, right? But that implies that the 4 minus 7t must be 0, right? And to solve that for t, that implies that t must be 4/7, right? So that's kind of telling you the scalar multiple you need to get to that point. So now all I have to do is plug that t in for this, this, and this. So we now find r of 4/7, which is going to be a vector, right? We already know what happens here, right? We get what? 0. That's the whole point, right? We wanted the x coordinate to be 0. Now, the rest, because I made this problem up, are going to be nasty numbers. We'll probably have to get a calculator and figure them out. But let me get my calculator. Let's go ahead and figure it out. If I have it, I think I do. Yes, there it is. And the batteries work. That's good. So I'm just going to my calculator. I'm going to do -1 plus 6 times 4/7. And then I'm going to do 2 plus 4 times 4/7. And that's going to give me that. So divided by 7, minus 1. So I'm getting 0. This is an approximation, about 2 point, let's say 43. And then over here, whoa, 4.29. Anyone else get that? No? Yeah. Anyone try it? 16 divided by 7 plus 2. Yeah. And then that's 24 divided by 7. Oh, wait a minute. Hold on. 24 divided by 7 minus 1. Oh, I think I did that right. Yes?
Would the final answer be like those normal like round brackets?
No. So this is the vector, right? If we wanted to know where it hits, we would write it as a point. Is that what you're asking me?
Yeah, but is that not what it's asking? Like where it hits?
Where it hits. So if I say it hits at a vector, vector can move around, right? So I want to actually know the x, y, and z coordinate of this point where it hits, right? So I would want my answer written this way. Where does it intersect? At the point 0, 2.43, 4.29. Is that what you're asking me?
Yeah.
Yes.
We're supposed to use round brackets.
Yes, because it is a point, not a vector. Yes?
Maybe with fractions.
Mm-hmm. Oh yeah, you could leave it as a fraction. This problem it was nasty because I just made it up, so the numbers didn't work out clean. All right, so given 2 points, we can find the vector equation of the line through that. We can also find the vector equation of the line segment connecting one to the other.